All right, so I'll introduce myself. I'm a PhD student pretty early in my degree. My supervisor is Mohammed Abdulaziz, who also presented in a seminar series about combinatorial optimization. And Thomas Ahmed, who's sitting there, also presented about combinatorial optimization and is another PhD student of Mohammed Abdulaziz. Okay, so let's go. My research areas currently are automated planning, specifically something called Temporal Propositional Planning, and PDDL, the Planning Domain Definition Language. I'll also present model checking and automata theory a little bit with respect to timed automata, because this is necessary to present the current project, namely the unsolvability of planning problems, which is a work in progress, I'm afraid. Scheduling. Well, okay, this is a simple automated planning example, right? What's automated planning? It's a representation of relevant and known facts. So in this case, the problem consists of two connected rooms, a robot in a room with a box in the same room, and the goal is to move the box to the other room. Very simple. So what does a plan look like? A temporal plan, actually. A plan is a schedule of actions. So actions have durations. You take 2 seconds to pick up the box, move to the other room, that takes 5 seconds, and then you put down, or the robot puts down the box, and it takes 2 seconds to do that. This demonstrates that planning is somewhat related to reasoning and problem solving using the rules which govern the world, namely that the robot can pick up a box. Okay, so let's summarize what automated planning is from this example. Automated planning or planning is concerned with the symbolic representation of complex problems and automated reasoning to solve problems. And my current work in progress is concerned with the planning domain definition language, PDDL. Specifically, I formalized its semantics in Isabelle, or the logic. I think you should know Isabelle. And with respect to abstract formalisms, right? And by doing that, it will easily lead to an application to, in certifying the unsolvability of planning problems. So now we're moving on to model checking. What's model checking? It's a formal verification technique. It's concerned with the correctness of computer programs or systems. It does, the first step is to model the system as a finite set of states and transitions which connect the states, right? And then properties are asserted over sequences of states, possibly of infinite length. We don't need to go into too much more detail, but like, for example, properties can be expressed in computational tree logic, CTL, or timed computation tree logic, which we don't need for this presentation. But here's some CTL examples. A phi until psi, in every path tree or trace, phi holds until psi holds, or e.g. Phi. This is a trace in which phi always holds, or AF phi. Every eventually satisfies phi, which you should probably remember if you don't know it, but yeah. So AF phi, we need this. What does it actually look like in practice? Right, here's a transition system. It's a cryptic structure, states and properties. For states, some transitions, and we evaluate CTL with respect to the computation tree logic, right? Transition to them, and we unwrap the whole thing and check which states are repeated, and we essentially, or a model checker essentially exhausts every possible path, or some simulation of every possible path. So these properties on the left are, well, satisfied, AG, P, or Q, because every state has P or Q in it. And AG, A, P until R is not satisfied, because it's possible to just transition to state 2, right? From state 1, and so on. Okay. So how does this project relate to model checking, right? So if you recall, the previous state space was discrete. We had 4 states, but some continuous state spaces, namely those with time, expressed in time as timed automata, can be model checked by discretizing and finitizing them. Okay, so The goals are to reduce temporal planning to timed automata. And then to use a formally verified model checker as a planner, which can check for and certify unsolvability. Right? This is an unsolvable problem because somehow we duplicated the block. And we don't want that. Or we want to be able to show that this is impossible. How do we do that? Or why do we want to do that? Like, look at this planning problem. We have 2 robots, 2 blocks, 4 rooms, and they can execute actions concurrently. We need to visit every relevant state to check for unsolvability, but which states are really repeated or equivalent when time and concurrency are factors? We can see these are the same, but they occur at different times relative to the initial state. And how we get there is not the same. So what actually happens here when we have 2 concurrent actions? And the answer to these questions lie in timed automata. And another question is, can we trust the planner, which claims something about this planning problem? The answer is not easy, but we can increase trust using certification. Or, well, another term, what is certification or program checking? Right? The diagram on the left simplifies it. The quote on the right by McConnell, Mehlmann, Schweitzer, and so on describes it, right? A certifying algorithm is an algorithm that produces with each output a certificate or witness that the particular output has not been compromised by a bug. And again, it's about program verification or program correctness. And it relates to testing and formal verification in almost a hierarchy, again, from the same source. So testing checks the program executes correctly on certain predetermined inputs and outputs. Certification executes the program and checks it afterwards. And formal verification doesn't execute at all. It just produces an argument that the program must behave in some way due to how it's structured. And why do we want to certify? Why do we need certification in this project? So ideally, if we check the certificate, it's faster than repeating the entire program or algorithm that produced the result initially. It should increase the trust we can place on the program because we have a checker which now claims that the program executed correctly. And if we verify the checker, which should be simpler than the original program, we increase trust without putting more effort in the verification of the original program. So let's summarize the project before we go into more detail. The goals are to characterize temporal planning in terms of timed automata, which I'll go into detail about more. And then we want to output and check Monta certificates of unsolvability. Okay, another term. What's Monta? Some existing work. A verified model checker by Simon Wimmer and Joshua Famutius. And another piece of work we'll start with is the formal syntax and semantics of PDDL 2.1 in Isabelle by Mohammed Abdulaziz and Lucas Koller. So what are we adding to this? A verified executable reduction from temporal planning to timed automata. Namely this one by Gigante and others, defined in 2022. And this one because this one didn't really work. I'll talk about it later. All right, so what's the current state? It's a bit of a mess. So here's the PDDL formalization I mentioned before. Here's the model checker and certificate checker, because of how it works, it's one thing. But yeah, we need to grant PDDL, represented in Isabelle, and then reduce it to a network of timed automata to be put into a unverified model checker, which should output a certificate of unsolvability of some problems or solvability, which can then be, well, the certificate can then be checked with respect, to the network of timed automata. Why do we do this? Well, initially I started with an abstract formalization of a reduction from temporal planning to updatable diagonal timed automata. And I wanted to just compile that to a network of timed automata. but that was a dead end. So instead, we're going from currently a ground PDDL file to a JSON file which represents a network of timed automata, and then we're running the model checker and certificate checker. And these parts are more or less done, depending on how solid the lines are. But okay, I'll go into more detail later. So the rest of this presentation, more detailed account of automated planning and PDDL, timed automata and model checking, and temporal planning to timed automata, well, the reduction, and some final thoughts. So let's recall automated planning or AI planning. Symbolic representation problems and reasoning in a domain-independent manner. Good. Automated methods to solve problems, okay, PDDL, and temporal propositional planning, which is an abstract formalism to describe the semantics of PDDL. Let's start with PDDL. So yeah, in PDDL, a world is defined with respect to some predicates and functions which have parameters. And this is actually not one world or domain, but this is like a class of domains. And moreover, in domain files, we have actions which could be thought of as like little programs which have conditions and effects. Effects can only occur when they start and end, and they have durations and they have parameters. Right? This is the action corresponding to a robot picking up something. We need to lock and unlock some variables, so we don't have contradictions in the state. Same thing with putting things down and moving the robot. Right, we have parameters. What does a concrete problem look like? Or the one that we've seen before in the pictograms, like this, right? We have a few connected rooms. We have the robot in one room, the blocks in the same rooms, and yeah, the other, and some functions which define how robots can move. And then we have the goal, which is unsolvable, right? But how do we actually describe how PDDL behaves? We reduce it to temporal propositional planning. We combine the domain and problem into a problem. We combine predicates and objects or arguments into propositions. The action schemas that we've seen before, with arguments to temporal actions, and then logical conditions need to be grounded into set-theoretic conditions, which are essentially big conjunctions of conditions. And because we also have disjunctions we need to reduce conditional actions to sets of actions combined with their conditions. And a goal condition is turned into multiple goal conditions, more or less. Okay, so not much detail yet. I'll get into more detail later, but yeah, PDDL isn't all there is to planning. You can plan by reducing it to Boolean satisfiability. There are some Markov decision processes, for example, which are formalized. These do planning in probabilistic domains. I'll point out these two pieces of work because this is where we're starting off with, and this is what defined PDDL initially, or PDDL 2.1. Okay, so what's temporal planning? A schedule. We schedule actions at times t with durations, and these somehow interact with the world when they start and end. Okay. Semi-formal definitions, sorry. A planning problem has propositions, durative actions, an initial state consisting of propositions, and a goal consisting of propositions, which must be satisfied at the end. A durative action consists of two snap actions, an invariant or an overall condition, and a lower and upper bound for the duration. A snap action has the conditions and additions and deletions. So a snap action is applied to a state, but before it can be applied, we need to check that the conditions are valid, and then we add and delete some propositions from the state. Okay, how do we formalize it? We fix all of these as functions on arbitrary types. We fix these in a context or locale, which is like an unnamed environment, and then we can implement them later and add some assumptions later, which make the formalization easier, I think. I'm not sure whether it actually makes it easy. Okay, actually, some assumptions are just provided by other packages when you create a concrete data type, for example. Okay, so what's a valid plan? A valid plan starts at the initial state and ends at the goal state with no actions running. Okay, how do we define that? We define a happening time point sequence. We extract every snap action into a set paired with the time points. And then we take the order time points, and then we extract these happenings, the sets of snap actions, and then we apply them all to go from one state to the next. What does it look like formally? Okay, here's a plan. A temporal plan is a function from an identifier, like an index in an array, to a pair of an action with a time and a duration. So yeah, this is what the previous slide looks like. What's interesting about it is actually the mutual exclusion condition, which can be summarized as no moving targets. So no two snap actions occurring at the same time, whatever same time means, can cause an uncertain result. So they can be applied in any order when it's scheduled for the same time point. But how do we actually formalize it? It looks like this. There are two conditions defined by Gigante and others in 2022, namely epsilon and zero separation. So epsilon separation quantizes the time into like intervals of size epsilon. No interfering happenings can occur with an epsilon, and zero separation just states that no two interfering happenings can occur at the exact same instant. And then we have some edge cases where, for example, the duration of the action is less than that epsilon, and that in that case it can interfere with itself. And this is hard to work with for the formalization, so add a few assumptions, and we go to discipline, which works on the happening sequence B, which we defined previously. Namely, the assumptions are that at start and at end are injective. Why? Because in the informal proof, we Gigante only refers to snap actions by these annotated actions. So we actually just instantiate snap actions with that. Well, in separate locales or contexts. Okay, sorry. Okay, we need to move on. So what's a valid plan? A valid plan is essentially a certificate, right? We can retrace it to say that the problem has a solution. How can we detect and certify an unsolvable problem? Well, by reducing it to timed automata, which we can then model check. This is actually implemented by by some authors of this original paper, which reduces planning to timed automata in a terminating planner, but not certifying. But to understand that, I need to introduce timed automata. Okay, timed automata are defined. Firstly, we need to define a time transition table, an alphabet, locations, and a transition relation, and some invariants on the locations. Okay, what does it mean? What's an actual state in a time transition table? It's a pairing of a location with a valuation of for clocks which assign a value to the clocks. And the transitions will check some constraints on the clocks and updates, and depending on which operators we allow in constraints and updates, it defines different classes of automata, but this is too much detail to go into right now. So the transitions are actions, right? Read a symbol, satisfy the constraint for all clocks, and then update the clocks. Reset them in simple timed automata. And delays, which just increment every clock. So a timed automata can do something or wait, to summarize. Yeah. So model checking timed automata, right? Again, model checkers can check a subset of timed computational tree logic that we mentioned before. And because timed automata define an infinite state space, we need to make it discrete and finite by partitioning the clock valuations. And again, how that is done is best left to others to explain. And then there are some optimizations which work with certain properties, like subsumption abstraction. Not what I need to talk about. So here's some relevant formalizations of timed automata theory, and the specific one that I'm using, namely the verified certification of reachability checking for timed automata, and some theory. Right, this is the reduction that I was talking to before. We number every action from 1 to n and propositions from 1 to n. Then we encode propositions and other binary variables in clocks. So whether an action is active or inactive, and then, yeah. So there's a main clock which records time, and binary variables are decoded with respect to that main clock in this section. Then we also encode other values in clocks. But okay, this section picks a set of snap actions and schedules them to be executed. And this section executes them and checks invariants that are active. The initial transition encodes the initial state, and the final transition checks that the goal is satisfied. To summarize this is actually like a while loop or like a program which non-deterministically picks valid snap actions and schedules them. Okay. So how are propositions decoded? Yeah, we check what their value is relative to the main clock, and then we reset them to constants. And this is what caused some issues, actually. How are things execute? How do we pick actions to be scheduled? We check the preconditions. Yep. Yeah, we check the preconditions. We check that they're not running, or that when we schedule them, we check that they must be running, and then we check that none of the interfering snap actions can have been scheduled for the same instant or within an epsilon. This is why we came to the mutex condition previously, which was a bit tedious to work out, I think. Yeah, and when applying effects, just apply them, add things and delete things from the state with updates. Constant updates to 1 to set things as true and 0 to set things as false. Sounds good. And yeah, I've formally proven that there exists a path from L0. No, if there exists a path from L0 to L star, the final state. No, sorry. If there exists a plan, there exists a path from L0 to L star, namely the final state. And if we can't reach the final state, there exists no plan. The contrapositive I've not proven because there were some issues, right? The diagonal clock constraints I mentioned previously to decode the binary variables and the updates to 1 are not directly compatible with the model checker. So yeah, because there are a way to encode clocks, to encode variables as clocks. And there's no easy way to really compile timed automata with diagonal constraints, and it takes simple timed automata. And maybe the question I should have been asking was, how do model checkers, which check real computer programs, concurrent computer programs, handle variables? Or how does the one that I'm using, or I should be using, do it? The operational semantics, which I mentioned previously, namely states being pairs of locations and clock valuations, are not correct. Well, they are correct, but a different one is used by the actual time model checker, which takes the valuations of variables into account. So instead of what we had previously, we also need to record values of variables for actual states. And moreover, Monta checks a network of timed automata. Yeah, so we need to use a different, or we don't need to use a different reduction, but a different reduction is also suitable. One which directly reduces planning to a network of timed automata. So rather than reducing planning by implementing a non-deterministic planning algorithm, we just consider each action as a concurrent process and schedule these, right? Boolean variables are just supported by the model checker. Invariants are no longer checked, but locked by incrementing a counter for each proposition and decrementing it. And yeah, the conditions are checked and effects are applied when we transition into these locations, which correspond to the instance when snap actions occur. So what have I done with this? I've implemented an executable version and tested some example problems. And it works. I can output a certificate and check it with a verified model checker, but the reduction itself is not verified yet. Because if you recall the diagram from before, yeah, we need to actually reduce ground PDDL to temporal planning, which, yeah, they're close, but not exact. So some final thoughts, right? What made this project very, or easy, more not easy, I mean, what helped me complete this or work on this project? Isabelle frameworks, data types, containers, and random transfer, the existing formalizations to learn from Monta and the formalization of PDDL. And what have I learned? Perhaps approaching things from different perspectives will reveal something, namely approaching planning as model checking revealed the exact mutex conditions, and maybe approaching planning as model checking from two different perspectives, namely via a planner or a scheduling problem, can reveal some things. And there's also a question which I've asked myself, is it possible to implement a certificate checker for timed automata with diagonal constraints and updates? Because Wimmer and Mutius have modified t-checker to generate certificates. Someone else, Mukherjee, has model updatable diagonal timed automata with t-checker, which is no certificate checker and no certifying algorithm. But maybe that's for somebody else to answer. Thank you.